So we're going to get started with RLC circuits and resonance. Welcome back, frequency chasers and circuit sleuths. You're tuned into another episode of Current Mysteries, the Electric Files, where the Electric Files, that's a good one, where every waveform has a secret. I kind of make these things up once in a while. And every secret has a resonance. I try to make this nice. Today we're stepping into the world of RLC circuits where we have resistors, inductors, and capacitors, and they don't just sit quietly in the loop. No, these three collaborate in dynamic tension, sometimes in perfect harmony, sometimes in sharp discord. And when they align, something strange and powerful happens. We call that resonance. In this chapter, we're going to unravel what makes an RLC circuit different from the RL or RC that we've covered so far. We're going to talk about how resonance can lead to maximum voltage or current in surprising places, and why this balance between reactance and resistance matters in radios, amplifiers, filters, and a whole lot more. This isn't just about math, it's about tuning into the natural frequency of a system and understanding what happens when everything clicks. So grab your notebook or just your curiosity, and let's dive into this chapter in Principles of Electric Circuits, RLC circuits and resonance. Are you ready to find the frequency where it makes sense? Let's begin. Impedance of series RLC circuits. All right, listeners, now that we've tuned into this chapter, let's go ahead and dive into the heart of the matter. Impedance in a series RLC circuit. So picture this. You've got your resistor denoted by R, inductor denoted by L, and the capacitor, which is denoted by C. All are linked in a single chain. Now, the inductor and the capacitor, like two cosmic forces pull in opposite directions. The inductor resists changes in current, storing energy in magnetic fields, while the capacitor stores energy in an electric field, resisting changes to voltage. And the beauty, well, the reactances, which is X sub L and X sub C, actually try to cancel each other out. And the result, well, we define the total reactance as the absolute difference. So X subtotal is equal to the absolute value of X sub L minus X sub C. Now, here's where things get interesting. If X sub L is greater than X sub C, your circuit is inductive, or it behaves inductively. But if X sub C overtakes X sub L, your circuit becomes capacitive. And you might already see this coming. So when X sub L equals X sub C, the reactances perfectly cancel out, and something very, very special happens. We call that resonance. But we're going to get there soon. Let's not jump ahead. But for now, the interplay between the inductor and the capacitor isn't just math. It's an electric tug of war. One stores energy in a field that twists, and the other in a field that stretches. And that balance point, well, it's where the magic of the RLC really begins. So stay tuned because in the next segment, we're going to uncover how these reactances shape impedance phasors and how these phase angles whisper the secrets of circuit behavior. Impedance of series RLC circuits. This is slide 2 of 10. So welcome back, circuit sleuths. If you're just tuning in, we're deep into the mechanics of the series RLC circuit. And now we're going to give impedance a proper mathematical identity. So the last time we talked about reactance cancellation between the inductor and the capacitor, but now let's put some real math behind that intuition. So in complex form, the total impedance, Z, of a series RLC circuit is Z is equal to R plus J X sub L minus J X sub C. And this is saying that we've got resistance from R, inductive reactance from X sub L, and capacitive reactance from X sub C. Since the capacitor's reactance is out of phase with the inductors, we subtract it, and that leaves us with a complex number, a real part R, and an imaginary part X sub L minus X sub C. But what if we want to express Z in polar form? You know, magnitude and angle? That's where things get really exciting. And I love math. So we're going to go ahead and write that as you see there on the slide, Z is equal to the square root of R squared plus the difference between the capacitive, between the reactances squared. So X sub L minus X sub C squared. And we square root that whole thing. And for the angle, it's the inverse tangent of the reactances over resistance. So it will be x of L minus x of C on the top divided by R. Again, doing the inverse tangent of that will give us the angle. The magnitude of Z comes from good old Pythagoras, and the angle tells us again how far out of phase the current is with voltage. And if you're feeling a bit of deja vu, don't worry, you're not in the matrix. This is because this should remind you of how we handled RL and RC circuits earlier. And here's a tip. When x of L equals x of C, that angle becomes zero. The impedance is purely real and you've struck resonance. Think about Neo and Agent Smith canceling each other out, leading to the real, right? That's not what the movie was about, but if it helps, it helps. So stick around because up next we're going to graph this impedance and show it um, elegantly. We're going to map it out on a complex plane. And again, things are just getting juicy. That's the only word I could think of. Impedance of series RLC circuits. This is slide 3 of 10. So again, welcome back everyone. Let's roll up our sleeves because today we're diving into a real circuit with real numbers. And yep, we're working that impedance math. So here's a setup that they give us. We've got a 470 ohm resistor. We have a 330 microhenry inductor and a 2000 picofarad capacitor, all in series and humming along at 100 kilohertz. This is all given. So this exact circuit will follow us through a few more slides. So make friends with it now. We start by calculating the reactance, right? Let's start off with the inductive reactance, where X sub L is equal to 2 times pi times the frequency times the inductance, which is 2 times pi times 100 kilohertz times 330 microhenries. That's going to go ahead and give us 207 ohms. Calculating the capacitive reactance the same way, the formula for X sub C is equal to 1 divided by 2 times pi times frequency times the capacitance. And again, that's going to give us 796 ohms. So the total reactance, if we calculate it, is X total being equal to X sub L minus X sub C. So we just subtract 207 minus 796, and we get a negative 589 ohms. Can we have negative resistance? Not in the real world, but in this case, it's just telling us that capacitive reactance is greater than an inductive reactance, and that's going to play a part into how the whole circuit works. So I don't want to give it away yet. No spoilers. Oh, I'll try not to give spoilers. So we write the impedance in rectangular form first. Z is equal to R plus J, X sub L minus X sub C. And we already know these numbers, so it's going to be 470 minus J 589, and all of this is in ohms. And there's our rectangular form for impedance. That negative imaginary part I was telling you about, it tells us the circuit is capacitive. The capacitor is dominating this frequency matchup. But now let's swing that impedance into polar form, which makes it easier for future calculations. So converting that to polar form, which we're not going to go over in the how to do that, we should have learned how to do that by now. Z is going to be equal to 753 ohms at an angle of negative 51.4 degrees. That angle, negative 51.4 degrees, confirms what we suspected. The voltage lags the current, which is classic capacitive behavior. All right. A quick tip here is as we keep moving forward, this impedance will be the foundation for calculating current, voltage drops, phase angles. And I said no spoilers, but a spoiler alert, even resonance. So hang on tight. This circuit is our tour guide through the rest of this podcast. All right. I'm just going to keep saying podcast. Impedance of a series RLC circuit, slide 4 of 10. All right, listeners, if you're just joining us, which you shouldn't, but just in case you are, we're deep into the world of RLC circuits, and we're peeling back the layers of impedance behavior. In this slide, it brings us face to face with an idea that's both simple and powerful. How frequency shapes the nature of the circuit. Let's go back to our earlier example. So remember that our calculated total impedance, it had a negative imaginary component. Right? It's imaginary and it's negative. Wow. Like, can things get any more Weird. But anyway, let's keep going. Anyway, what that did is it pointed to us that the circuit behaves capacitively, right? Overall, it behaves capacitively. But why? Oh, well, here's the secret sauce. It's all about comparing the reactance of the inductor, X sub L, and the reactance of the capacitor, X sub C. So when X sub C is greater than X sub L, the total reactance goes negative, meaning the capacitor dominates. When X sub L is greater, the inductor wins and the circuit becomes inductive. Now look at the graph on the slide. The X sub L line climbs upward with frequency. The X sub C line drops downward with frequency. So at low frequencies, X sub C is high and X sub L is low. Capacitive behavior dominates here. But crank up the frequency and eventually X sub L overtakes X sub C, flipping that script to inductive. So what's the takeaway? A single RLC circuit can change its personality, capacitive or inductive. Does that sound like someone you know? I don't know. But we all know someone like that. So just by changing the frequency, we can change the behavior of the circuit. Think of it as a mood swing powered by Hertz. In our example, the frequency was such that X sub C was greater than X sub L. We said that it was that was capacitive behavior. And so yes, it's still one physical circuit, but it reacts very differently depending on how you drive it. Kind of like how your microwave or your Wi-Fi router, they don't get along when they're on the same channel. So with that said, stick around because we're about to explore how this balance point where X sub L equals X sub C. And this leads us right to something called resonance. Impedance of series RLC circuit, slide 5 of 10. Welcome back, learners and listeners. We're continuing our journey through RLC circuits, and this time things are heating up. Literally, quite literally, because now we've raised the frequency, and with it, the behavior of our circuit has changed. Let's dive into some numbers now. We're still using the same components where R is equal to 470 ohms, the inductance is 330 microhenries, and the capacitance is 2000 picofarads. But this time the frequency is cranked up to 400 kilohertz. And let's go ahead and redo our calculations. X sub L becomes 829 ohms. X sub C drops to 199 ohms. And that gives us a total reactance of X sub L minus X sub C, which is going to be equal to positive 630 ohms. So now you can see that the imaginary part is positive, and our impedance is Z is equal to 470 plus J 630 ohms, which in polar form is going to be 786 ohms at an angle of positive 53.3. What does this all mean? It means our circuit has flipped from capacitive to inductive, and think of it this way. Earlier at 100 kilohertz, the capacitor was dominating the dance floor, but at 400 kilohertz, the inductor has taken over, spinning with higher reactance. The phase angle is now positive, telling us that the current is lagging the voltage. So we have a classic sign of inductive behavior. This is kind of like the beauty of AC analysis and RLC systems. Frequency isn't just some number, it's a dial that changes how the circuit behaves completely or entirely. Um, I'm, I'm hesitant to make references to Neo and Agent Smith here because I don't want one of them to be Agent Smith or Neo. X sub L and X sub C, I have a spot in my heart for both of them. So for now, stay tuned because next we're going to see what happens at high resonance when X sub L and X sub C cancel each other out. That's when things get very, very interesting. And I think that was the end of the Matrix movie. But let's continue. Cadence of series RLC circuits, 6 of 10. Welcome back, tech travelers. So far, we've seen how an RLC circuit can go from capacitive to inductive behavior just by changing the frequency. In our last episode, we bumped the frequency up to 400 kilohertz, and voila, the circuit went inductive because X sub L was greater than X sub C. Now, here's where we take it a step further. What we're looking at is the frequency response of this circuit here on the slide. So how the inductive reactance, which is X sub L, and the capacitive reactance, X sub C, evolve with the changing frequency. And guess what? You don't have to sketch it out by hand like it's 1955. I think there was a song. Nah, forget it. Forget that pun, right? Or that reference. This is where your TI-84 calculator comes into play, or any calculator. Again, since we're mentioning the Texas Instruments calculator, I think it's just to be fair to mention my favorite calculator, the Hewlett Packard HP 48. All right. Anyway, let's continue going. So yes, your trusty graphing calculator, whichever one it happens to be, dig in your backpack and um, pull that out because it's about to become your best friend, your frequency analysis assistant. On this slide, I'll walk you through the exact steps to plot XML and XMC curves. And yeah, so hang tight, pull out your calculator, fire up the Y editor, and I'll guide you through the setup in the next segment. So next up is going to be graphing the frequency response with real data. Stay tuned and catch you on the next slide. Students of Series RLC circuits, 7 of 10. All right, welcome back, Frequency Explorers. We've talked theory, we've looked the math, and now it's time to get hands-on, right? In this slide, your map into visualizing how impedance and phase angle shifts as you change the frequency, and we're doing it with your trusty calculator, whichever one it happens to be. But I'm going to give you the instructions for the TI-84. So let's set this up like a pro. You'll start by entering the equations for y sub 1, y sub 2, y sub 3. So remember, y sub 1 is for capacitive reactance, y sub 2 is for inductive reactance, and y sub 3 is for the total impedance. And optionally, excuse me, y sub 4 for the phase angle theta. Your independent variable here is x, which will represent frequency, and think of x as your dial. You'll be turning it up and down to see how the circuit reacts. And here's a cool part: you can reuse equations you've already typed. Just hit the VARS key. Again, that's not voltage amp reactive as we talked about in power. This is the variable key. So choose Y variables or VARs. Go to the function, grab Y1 or Y2. This makes the equation building super efficient. And let's say you're entering Y sub 3, our impedance formula, where you're basically squaring the difference between Y2 and Y1. So that's X sub L minus X sub C. And then adding R squared, which in this case is 470 ohms squared. And then you take the square root. But don't worry, if Y4 isn't plotted just yet, you can come back to that one later when we focus specifically on phase shift. Now here's a tip. Double check your constants. So we said capacitance C is 2000 picofarads, inductance L is 330 microhenries, and resistance R is 470 ohms. Go ahead and enter that, hit the enter button, and boom, you're graphing real world physics on your calculator screen. But up next, we're going to fine tune the plot settings and watch those curves come to life. So stick around. We're only getting started. Impedance of series RLC circuits, slide 8 of 10. Sometimes I feel like this is the take, what do they do in movies when they say action and they do the little thing? So I should have that. Impedance of RLC circuits, slide 8 of 10. Action. Okay, so welcome back, tech tinkerers. Last time we dove into plugging in math for our RLC circuit. Now it's time to prep your TI-84 like a pro so that it displays the frequency response you've been calculating. In this slide, it's all about setting up your calculator's graphing window to actually visualize those reactance curves. So this is what you're going to do. Go ahead and press the window key to bring up the graph parameters. Set Xmin to 0. Set Xmax to 528,000. And this is your frequency range. It's perfect for exploring from 0 hertz all the way up to megahertz territory. The X scale, set that up to 50,000. This gives you evenly spaced tick marks for frequency, not too dense and not too sparse. Go ahead and set up your Y min for 0 and your Y max for 1,000. And that's your impedance range. You're looking to graph values up to 1,000 ohms. And then your Y scale, set that equal to 100. Same idea. This gives you a good visual clarity on the Y axis. Now, this is the crucial part. Set delta X equal to 2000. And that's how tightly you want to sample data points. But don't sweat the X max. If you give the calculator the X min and the delta X, it'll auto calculate X max for you. So again, in short, this whole thing just sets up the stage for a good crystal clear curve to show you X sub L, X sub C, and Z for impedance. Remember that the TI-84 isn't just crunching numbers, it's painting an electrical picture. So get your window dialed and let's zoom into the results next. Stay tuned. Next up is the graph magic moment. I just gotta make one more comment here. I've talked about the turning electrical engineering into some composition of music, and as the electrons dance around, where signals go up and down and filtered and everything. Uh, but I'll see if I can make some artistic drawing, painting type of references from here on out, because that just seems to fit this slide perfectly. Impedance of series RLC circuits, 9 of 10. Action. So, welcome back, circuit sleuths. In our last session, you tuned up your graphing calculator to visualize how reactance and impedance shift across frequency. And now it's time to hit the graph button and see your math come alive. You're an artist, you just didn't know it. In this slide were all those expressions for x sub c, x sub l, and then z finally show up on screen. And this is what you're going to do. Go ahead and just press the graph key button, and boom, you're going to see the three crisp curves. The red line represents X sub L. Remember, that's inductive reactance. That climbs as frequency increases. The blue curve is X sub C. That's capacitive reactance. That drops as frequency rises. And the green curve, that's your total impedance. Right now, it's curving right down to a minimum at resonance. And here's a good sweet trick for this. Press the trace button to move a cursor along the curve. And what you can do is you can read the exact impedance at any point, like say 400 kilohertz, for example. If you want to label your graph also for a class presentation or lab report, you can also press the second function key, the program key, to open up the draw menu and annotate your graph like a pro. This is a moment where theory meets the screen, where paint meets the canvas. That's what I got to do. I like the paint meets the canvas analogy here. You're not just crunching numbers, you're mapping how energy flows through reactive components. You're also painting this beautiful picture of the frequency responses here. Up next, we're going to wrap this up with resonance and talk about what happens when X sub L and X sub C balance perfectly. So don't miss it. Voltages in a series RLC circuit. All right, listeners, pulling close for this one. If you've ever wondered how voltages dance their way through an RLC circuit, this is your front row seat. On this slide, we're going to break down what happens when voltage meets Kirchhoff's voltage law in a series RLC system. I bet you thought you were never going to see Kirchhoff's voltage law again, but it's going to follow you for the rest of your career. So let's go ahead and talk roles, right? V sub L, the inductor's voltage, is your high energy overachiever, always leading the current. V sub C, the capacitor's voltage, it's the chill one, it's in the back, it's lagging behind the current. And the resistor, it's neutral ground, it stays in phase with the current. Now here's a twist. We said since V sub L and V sub C are 180 degrees out of phase, they subtract. And when you add them algebraically, well, you got it. That's right. Opposites don't attract here. They cancel out partially, right? So again, my reference to the Matrix, Neo and Agent Smith being complete polar opposites. If you didn't catch that mathematical reference in the movie, go back and watch it. So the result is a net reactive voltage that's smaller than either alone, but still enough to make the system inductive in this particular case. That's because X sub L is greater than X sub C, and the net behavior tilts toward the inductor's lead. So why does this matter? Because every RLC voltage waveform must add up to the source voltage, even if some of the components are out of sync. It's a perfect example of Kirchhoff's voltage law in action, right? It never goes away. It's universal in all and for the rest of your electronics career. Again, unless you're somehow living on the event horizon of a black hole, and I actually couldn't tell you what happens there. None of us can, but we can speculate. But luckily, none of us are in the event horizon of a black hole. So let's go ahead and continue with our understanding of this here. Again, this is the type of voltage arithmetic that separates the hobbyist from the pro. This is what separates you from before coming to school, getting an abstract understanding of this to understanding this quantitatively. So stick around because coming up, we tune into resonance, pun intended. You won't want to miss that. Resonance revealed, slide 1 of 5. So you've been waiting for it, right? And here it is, series resonance, the electric sweet spot where everything just clicks. And so picture this. Close your eyes. Picture this. No, really, close your eyes and picture this. You have a series RLC circuit where the inductive reactance XBL and the capacitive reactance XC are perfectly matched. So what happens? They cancel each other out. It's like a cosmic balance. Positive and negative reactances offset each other like two equal and opposite waves crashing together in silence, or two opposites crashing into each other in the middle of a storm like the Matrix. And it was very fortunate that Neo and Agent Smith were equal but opposite. Otherwise, the universe in the Matrix would have ended up being one way or the other, and that would have been a catastrophe for everybody. So I'm sorry, let's go ahead and continue with the slide. So at this point, V sub L and V sub C, the voltages across the inductor and the capacitor, they cancel because they're equal in magnitude and opposite in phase. Their algebraic sum is 0. So what's left is pure resistance. No imaginary parts, no reactive drama, just clean resistive current flow. Uh, this is what we call the resonant condition, and it is gold for tuning circuits, also for radios and signal filters, and for ending a fantastic trilogy in the Matrix. But at resonance, your circuit is like a tightrope walker with perfect balance. So any shift in frequency and the dance is over. But while you're at resonance, you have smooth, efficient, elegant, movement. So with that said, stick around as we break down how to find that magic frequency and what happens when you stray from it. Resonance revealed, slide 2 of 5. Action. So, welcome back, Resonance fans. In our last segment, we talked about the magical moment when X sub L is equal to X sub C, and the classic highlight of the movie when Neo and Agent Smith actually cancel each other out, or when at least Neo realizes what has to be done. Right. So, the condition for resonance in a series RLC circuit um, means that X sub L has to equal X sub C, but in opposite polarities. So let's just go ahead and do some math, right? So we're diving into the formula for the resonant frequency, and again, it's one of the most iconic in electronics and one of the most iconic in the matrix. The resonant frequency denoted by F sub R is going to be equal to 1 divided by 2 pi times the square root of LC, uh, all in the denominator. So you can just look it up there in the slide. And again, that's it. Simple, elegant, powerful. There is a way to derive this if you don't believe me. Just go ahead and set the resonant frequencies equal to each other and then set X sub C equal to X sub L. Plug in their formulas, and you eventually will get, if you derive it, you're going to get this formula for resonant frequency 1 divided by 2 times pi times the square root of LC, right? Again, simple, elegant. And what this formula tells you is the frequency at which the reactive powers cancel each other out, leaving only resistance. So just plug in your inductance, L, and your capacitance, C. Again, no Ouija board needed, maybe an oracle or two, and voila. Right, so let's go ahead and look at the example. Right, you've got a 330 microhenry inductor and a 2000 picofarad capacitor. Drop them into the formula and boom, your circuit resonates at 196 kilohertz. And I was thinking of the boom where Neo and Agent Smith are up in the air and they go at each other, creating such an equal but opposite explosion that it actually stops the rain from coming down. Great movie, by the way. Um, anyway, that's the frequency where your circuit will behave like a pure resistor. And why does this matter? Because if you're building filters, or if you're building tuners, or even if you're building something like a guitar amp, which I think most of you know what that is, um, You know this frequency lets you maximize the signal. It helps you minimize noise. Basically, it helps keep everything humming along like a well-tuned instrument. Okay, so next time someone says, "What's your frequency?" you know exactly how to find it. Onward to the next voltage story. I'll try to stay away from too many matrix references. I promise. Resonance in action, slide 3 of 5, and action. Okay, listeners, let's take this resonance thing and put it to work. In this slide, this one's all about what happens to the voltages in your circuit when resonance hits. So here's the magic. At resonance, the voltages across the inductor, V sub L, and the capacitor, V sub C, are equal but opposite in phase. So again, equal in magnitude but opposite in phase. So when you add them up, bam, they cancel each other out. And that means that the total reactive voltage ends up being zero. Now, what does that leave us with? Well, it just leaves us with the resistor. And if the resistor is the only game in town, that means the entire source voltage must drop across that component. That's KVL, Kirchhoff's voltage law in action. So let's look at the example here. The source voltage here is given to us at 5.0 voltage RMS. And remember that V sub L plus V sub C is equal to 0 in this condition. So the full 5 volts drops across the resistor. So V sub R is going to be equal to V sub S, which in this case is 5.0 volts RMS. Again, so clear, so elegant. It's like electric poetry. This is a sweet spot of resonance. No reactive voltage, just resistance, and your signal flows smooth and strong. And that's it. So go ahead and catch your breath. We've still got a couple more slides before resonance really starts to dance. Resonance Unleashed, slide 10 of 10. Here we are, folks, the final piece of the series of this impedance puzzle. And wow, does it wrap things up beautifully. So let's go ahead and talk about series resonance, or continue talking about series resonance. And at this special frequency, something elegant happens. Remember, we said X sub C is equal to X sub L. Inductive reactances are perfectly equal and opposite, right, to capacitive. And because they cancel each other out, the circuit's impedance isn't influenced by reactance anymore. It's just purely resistive. That means the total impedance of your RLC circuit is now just R, nothing more. And you can see that moment on the graph, right? At the intersection of X sub C and X sub L in the curves. That's your resonant frequency, where the imaginary part of impedance vanishes and your circuit behaves like a simple resistor. Again, why does this matter? Because at resonance, current is maximized. So we know a special condition at this particular frequency. It's the most efficient condition for energy transfer. Your voltages are still oscillating, but the energy tug of war between L and C is perfectly balanced. Think of it like the universe snapping into harmony. For just one brief, beautiful moment, everything just clicks. And with that, we've come full circle. Reactance, resonance, and real world relevance, right? So go ahead and stick with us for the next podcast where we explore how this resonance principle power filters, um, oscillates, and more. So until next time, keep your circuits resonant and your thinking grounded. And I just figured out who the resistive analogy is here. So Neo and Smith are the reactive components, but when they cancel out, what does that leave? Only the real, which is, oh wow, that actually does jive a lot with the movie, which is the real people and the real machines, right? It's just the real stuff. So pretty cool. I didn't plan to go down this direction, but it works. If it works, it works. Tuning into resonance. This is slide 4 of 5. 4 of 5. Action. So welcome back, everyone. We're still exploring the magic of series resonance, and this time we're bringing in some digital help. Your friendly neighborhood TI 84 plus calculator. The TI 84 plus calculator could be like some of the help that Neo got in the movie, like the key maker. But this is not the key maker. It's got to be something else. One of those programmers that he met in the second movie. Again, so here's the situation. You've got an impedance curve for your RLC circuit, and you want to find the resonant frequency, the exact point where impedance hits its minimum. And this is how you do it. On the TI-84, go ahead and press the second function key, then press trace to access the calculate menu. From there, select minimum, and we're looking for the lowest point on the impedance curve. And there you go. Voila, the Merovingian, right? Voila. The calculator looks uh, onto that sweet spot. You know what? Yes, the TI-84 is the Merovingian, right? And so what does it show you there on the graph if you're following along? It shows us the resonant frequency is equal to 196 kilohertz. So at this frequency, your circuit's impedance is at its lowest, and you're going to notice something pretty awesome. That impedance is equal to resistance. Z is equal to R. And what does this mean? It means that the reactive parts canceled out perfectly, and your RLC circuit behaves like a pure resistor. And this matters because this is the heart of resonance. At this point, power transfer is most efficient, the current is highest, and the voltage across the resistors tells the whole story. This is a powerful technique, one that you're going to use again and again and again in the real world of electronics and in your design work in the future. So, again, with that said, hopefully that'll motivate you to keep sticking around because next up, we're going to look at what happens to voltage across each component at its resonant point. See you in the next wave. Visualizing phase angle, summary phase angle. I'm going to stop with the matrix references. I don't think I have any more, but we did pretty good with that. So again, welcome back, circuits loose. We've reached the part of our journey where things start to shift literally. And let's talk about phase angle. So my mind is still trying to make references to the matrix. I better stop. So what we're looking for here is we're plotting how the phase angle between voltage and current behaves across a frequency sweep. And so what a frequency sweep is that you're just shifting through a bunch of frequencies and you're seeing the response of something over a large range of frequencies. And because this phase angle doesn't sit nicely on the same scale as impedance, we've got to give it its own plot. So we're working from negative 90 degrees to positive 90 degrees with our x-axis as a frequency. So we're going to start from 0 going all the way up to 528,000 hertz. And on the y-axis, we're using a clean range of negative 90 to positive 90 degrees. The grid lines are spaced at 50 kilohertz horizontally and every 20 degrees vertically. That's going to keep everything relatively crystal clear so you can see. Um, on the right, on the slide here, you're going to see the actual curve plotted on the TI-84 Plus, and that tidal X cursor, it's sitting right at the resonant frequency, around 196 kilohertz. That's where our phase angle passes through 0. And again, you're asking, but why is this important? Well, because at resonance, the inductor and capacitor cancel each other out. Again, the oracle was right the whole time. She knew that. And the circuit's behavior becomes purely resistive. So she set him up, but she didn't tell him that. He had to figure that out on his own. But anyway, back to the slide here. This is why phase angle is 0. You have no leading, no lagging, just smooth, clean alignment between voltage and current. So remember, tracking phase shift across frequency isn't just math, it's an insight into your circuit's mood. And we're going to go ahead and break that down further in the next segment. So stay tuned and stay resonant. Wrapping up series resonance, right? The summary series resonance, slide 5 of 5, and action. And just like that, we've hit the resonance sweet spot where everything clicks, currents surge, and phasors chill out. Here's the quick recap of what series resonance means in a circuit without the matrix references. And we're going to talk about why it's more than just a buzzword. So first, this is where capacitive and inductive reactance are equal. Think of them like two dancers with opposite steps. They cancel each other out. Second, that cancellation drops the total impedance down to its minimum. And so what you have left is pure resistance. We're hoping to get it down to 0, not resistance, but the impedances. That way you're dealing with a pure resistive circuit. And so that just means that all the energy from your source can now flow freely. And third, with minimum impedance comes maximum current. So it's like unclogging a pipe that allows the flow to rush in. And fourth, and yeah, and fourth, the phase angle between the voltage and current, that goes down to zero. They're in sync. Again, this is going to tell us we have no lagging, we have no leading, just perfect electric harmony. And fifth, or finally, your resonant frequency. The magic point is calculated using the formula F sub r, which is the resonant frequency, being equal to 1 divided by 2 times pi times the square root of LC. Let me go ahead and give you a tip before we move on. That formula is your golden key to tuning circuits into radios, filters, and oscillators. So when you design with resonance, you're not just solving a math problem, you're tuning your circuit like a symphony. Um, that's it. I made a lot of references to the arts, right? To symphony, to canvas painting, to poetic to poems. That I think I will keep up. I'm going to go ahead and back off the matrix. But for here on out, just go ahead and stay tuned, stay curious, and I'll catch you on the next waveform. Let's catch some waves. That's good. Parallel thinking impedes a parallel RLC circuits. Okay, team, let's pivot our focus from series to parallel RLC circuits. This is a whole new beast, and one with its own rhythm. And here's the scoop. In a parallel setup, resistors, inductors, and capacitors are each dancing to the same voltage beat, but the current is where the complexity lives in parallel circuits. So to find the total impedance, we go ahead and flip that script. I can literally, we flip it, and the formula is 1 over Z, which is equal to 1 over R at an angle of 0, plus 1 over X sub L at an angle of 90, plus 1 over X sub C at an angle of negative 90. Again, so instead of adding the elements directly, we add their reciprocals because that's how parallel circuits play. This is like summing up individual flows into one stream, but each flow has its own direction, and that's where those angles come in. So now you can take the reciprocal of the whole thing to get Z. 1 over Z, you take the reciprocal, you get Z. Now that's total impedance. That's your final answer, but don't forget it. Don't forget, I'm sorry, that it's in polar form. Notice the phase angles here. The resistor sits at 0 degrees. That's because it's grounded, figuratively and literally. The inductor is at plus 90. Remember, that's because it's always lagging a bit behind. And the capacitor is at negative 90. It's way out ahead of the pack. So this trio forms a frequency-sensitive system. Just go ahead and wait till we explore resonance and parallel forms where things get even wilder. I'm sorry, I'm thinking of the trio, and I'm kind of thinking of Neo, Trinity, and Morpheus. I have no analogy for that. I just brought it up for no reason. If you all think of one, let me know. But that's it. That's it for now. Remember this, in parallel RLC circuits, impedance isn't just about straight lines. It's about balance, reciprocals, and smart phasor math. So catch you up on the next pulse. Parallel RLC circuits, a phasor breakdown. This is sinusoidal response, slide 1 of 3. All right, friends, it's time to break down the sinusoidal response of the parallel RLC circuit, where things start to split up and move in different phasor directions. Picture a dance floor, excuse me, close your eyes. You're not closing your eyes. Okay, good. You close your eyes. Now, picture a dance floor with 3 different styles going on at once, but they're all in sync with the same beat, aka the source voltage. Let's decode it. So Ohm's law still rules the show. For each branch, resistor, inductor, capacitor, we apply the I sub r is equal to Vs divided by R. Right? This one walks a straight line plotted on the positive real axis. Remember, resistors are always on the positive real axis. There's no phase drama here. We can look at I sub C, which is equal to V sub S divided by X sub C, or the capacitive reactance. Remember that capacitor current leads the voltage. It's always eager. That puts it up on the positive J axis in the phasor space. And then we have finally I sub L, which is equal to V sub S divided by X sub L, that inductive reactance. And with the inductor, yep, you guessed it, it's always lagging. So it lands on the negative j-axis. But together, these phasors form a triangle of motion, and the total current is the vector sum of all three of those. And that's the beauty of parallel design. One voltage, three distinct current flows, each with its own personality. So coming up next, we're going to see how these vectors add up and what happens when resonance sneaks in. So stick with us because the phasor party is just getting started. So RLC currents unite. The sinusoidal response, slide 2 of 3. Welcome back to Curves, Currents, and Capacitors. Last time we introduced our trio of phasors, resistor, capacitor, and inductor. Now let's see how they work together in one of the most visual and vector-rich ways, calculating the total current in a parallel RLC circuit. Now here's the key. These phasors are not in a straight line. They diverge into their own directions, some up, some down, one right across. So let's go ahead and check out the diagram where I sub r moves along the real axis, I sub c points straight up the imaginary axis, I sub l dives down into the negative j-axis. So what do we do with this mix of directions? Well, we vector add. So the formula for total current is I sub total is equal to the square root of I sub r squared plus I sub c minus I sub l, all that squared, at an angle of inverse tangent I sub CL over I sub R. Um, and let's go ahead and apply that to our example here. So in our example, they're giving us that I sub R is 10 milliamps, I sub C is 15 milliamps, and I sub L is 5 milliamps. The next vertical component is I sub C minus I sub L, right? So we just subtract those two, we get 10 milliamps. And this gives us this perfect 45-degree triangle. And what is the result? We have the total current of 14.1 milliamps at 45 degrees. And this tells us that the circuit is capacitive dominant. That extra current from the I sub C that pulls the angle up into the first quadrant. And so whether you're tracing phasors or you're sipping espresso, remember that in parallel RLC, direction does matter. So that's it. Next up, we're going to bring it all together, literally, in the total current diagram. Inductance, susceptance, and the parallel RLC wrap-up. This is sinusoidal response of parallel RLC circuits, slide 3 of 3. Action. Welcome back, engineers in training. You've been tracking phasors, you've been adding currents, and you've been analyzing the geometry of every signal swing. Now we wrap up our dive into parallel RLC circuits with a subtle but powerful concept, using admittance quantities to find the current. What? Yes, that's correct. Let's go ahead and break that down. We've already worked with resistance, inductance, and capacitance, but when it comes to parallel analysis, their reciprocals take the spotlight. So remember that conductance, G, is represented by 1 divided by R, and again, this stays on the real axis. Capacitive susceptance, which is B sub C, is defined by 1 divided by X sub C at an angle of negative 90, and this points downward in phasor space. And last but not least, the inductive susceptance, denoted by B sub L. This is equal to 1 over X sub L at an angle of 90 degrees, and this one points upwards. And the total admittance, you ask? Well, that's denoted by Y, and it's going to be equal to 1 over Z at an angle of plus or minus theta. This bundles them all into one complex entity. And here's the insight for this slide. Once you have these admittance values, they simply you can simply multiply the voltage to get current. That's right. So we're using Ohm's law, and Ohm's law carries on, but now in the reciprocal form. And this matters because in phasor analysis, using admittance just simplifies the addition of elements in parallel, just like impedance is useful for series. So if you're thinking, wait, we're just flipping stuff around? Yes, but that flip lets us solve complex parallel networks with clarity and with speed. Again, this wraps up our three-part arc on that parallel RLC sinusoidal response. And what's up next? where we're going to explore resonance in parallel configurations, and we're going to see just how dramatic things can get when phasors align, or they cancel, right? So until then, keep your phasors sharp and your vectors balanced. Parallel RLC currents, the push and pull of opposites. Welcome back, curious minds. We're about to witness one of the most elegant tug of wars in electrical engineering, the current dynamics in a parallel RLC circuit. So let's go ahead and set the stage. In any parallel network, Kirchhoff's current law reigns supreme. The sum of the branch currents equals the total source current, but that's where things get spicy. Our capacitor and inductor are always fighting out of phase. So the inductive current, I sub L, that lags the voltage by 90 degrees. The capacitive current, I sub C, that leads by 90 degrees. So the net result is that they point in opposite directions on the phasor diagram. What happens when these two phasors collide? Well, they subtract, not destructively, but constructively, revealing the leftover current that contributes to the total. The visual here is pretty powerful if you're watching waveforms, if you're looking at them. The capacitor's current crests early, and the inductor's current drags behind. Together, they create a dance that aligns beautifully with the resistor's straight and steady path. This subtraction by phase is how we unlock the total source current. That's just the current your generator would actually provide or supply. But go ahead and stay tuned. In the next segment, we calculate the complete source current. We break it down with phasors math, and we tie it all back to what your scope would see in real time. So until next time, keep calm and let those phasors flow. Visualizing current flow in parallel RLC circuits. This is slide 2 of 2. Alrighty team, let's continue dissecting the current flow in a parallel RLC circuit. If you're just joining us, go back and check the previous episode where we introduced the current phasors. This time, we bring those phasors to life on a grid, and trust me, the numbers tell a compelling story. We've got our players, I sub R, I sub C, I sub L, where I sub R is 12 milliamps, that's along the real axis. I sub C is 22 milliamps, that's straight up the positive axis. And I sub L is 15 milliamps, that's straight down the negative axis. So let's go by step by step. So step one, set your graph scale, right? 2 milliamps per division, that's about right. Plot each current at its proper angle, and then combine IC and IL. Uh, since they point in opposite directions, subtract them to get the net reactive current. So I sub L being 22 minus 15, that's going to give us, how much do we get? 13.9 milliamps. We can use Pythagorean theorem and the arctangent to find the total current magnitude and phase angle. That's how we got the first one, 13.9. But using the inverse tangent, we end up with 30.3 degrees. So this means that you have 13.9 milliamps at an angle of 30.3 degrees. That leads the resistor's current due to the excess capacitive behavior. And again, this isn't just math. It's a portrait of how your circuit breathes with alternating current, and each waveform you use on the oscilloscope is built from the phasors that we discussed and their relationships to each other. The next time you fire up that circuit and you see voltage, a voltage spike, or even a voltage dip, now you know. It's just the inductor and capacitor wrestling in time, and the resistor keeping the peace. So stay tuned. We're headed into resonance next, and that's where things get even more really rhythmic and more interesting. Welcome to Parallel Resonance. This is slide 1 of 4. Can you believe I'm doing all of this without coffee? I don't drink coffee. All right, so welcome back, learners. Today we're diving into one of the most harmonious concepts in AC circuits, and that's parallel resonance. Imagine this. Okay, I'm going to go ahead and pause until you close your eyes and imagine this. Okay, good. So imagine you got a capacitor and an inductor in parallel, both drawing current from the same voltage source, but something magical happens at just that right frequency. Right, their currents cancel out. And so at resonance, I sub C and I sub L are equal. And what's left is just the resistive component, I sub r. That's why we say that the circuit is purely resistive at resonance. What you'll see on the plot is I sub c rises as one wave and IL drops as its mirror image, and their algebraic sum hugs that zero line. This is the circuit at its most efficient. It's minimal reactive power. There's very clean behavior here, and you have a maximum calm here to this chaos. Now, what I want to stress is that minimal reactive power. We talked about this prior to here, and this is where it all comes into play. But don't forget, this is the opposite of what we saw in series resonance, where the inductor and capacitor voltage is canceled, right? Here, it's their currents. So parallel, it's their currents. Series, it's their voltages. We're going to keep making those same relations for from now to kingdom come. All right, so stick around as we explore how to identify resonance, how we compute it, and recognize what happens when you move away from this beautiful balance. So let's tune in, resonance style. Parallel resonance, slide 2 of 4. Welcome back. In today's episode, we're zeroing in on a key mathematical gem in the world of parallel resonance. Whether you're working with series or parallel RLC circuits, when it comes to resonance, the formula remains identical. It's classic, right? So you see there in the slide, F sub R is equal to 1 divided by 2 times pi times the square root of L and C. All right, that's that ideal case. This is your golden key, your golden formula, where resonant frequency, again, is that frequency at which inductive and capacitive reactances cancel out perfectly. Um, in the circuit example shown here, we've got an inductor with 680 microhenries, a capacitor with 15 nanofarads. Plug those into our resonance formula, and what do you get? Well, they tell you what you get here. The resonant frequency is 49.8 kilohertz. Again, follow along, type these numbers in your calculator. Make sure that you can actually get the same number that we do in the slide. Don't just observe, right? Do it yourself as well. So this is going to be our ideal case. And I emphasize ideal because, again, in the real world, resistors and other parasitic elements can tweak that value just a bit. But conceptually, for now, this is a moment when your circuit achieves perfect balance. It only happens in textbooks or in movies, right? So the inductive and capacitive forces are equal but opposite. They're perfectly equal but opposite. And it's like the equilibrium point in a ghost hunting episode. That eerie calm where all the energy is poised but nothing is wasted. Okay, so coming up next, we're going to look at what happens at resonance and how the current, the voltage, and the impedance all behave together. So stay tuned. The frequency's about to just get right. Parallel resonance, slide 3 of 4. All right, listeners, we've talked about the ideal resonance frequency, but let's shift the focus to what happens in real life circuits, where perfection takes a backseat to practicality. So here's the deal. In theory, right, the resonant frequency equals 1 divided by 2 times pi times the square root of LC, and that's all you need. But in reality, our components aren't perfect. That coil resistance, often overlooked, right, introduces just this tiny hiccup in the otherwise smooth symphony of resonance. It's like if you're listening to a symphony and somebody's just a little flat or a little sharp, if you understand music theory. So instead of relying solely on the ideal formula, engineers account for this imperfection using a non-ideal version of the resonance equation. And that is what you see there on the slide. Resonant frequency, again, still equal to 1 divided by 2 times pi times the square root of LC. But now we're going to multiply it by a factor, which is the square root of q squared divided by the sum of q squared plus 1. And this formula folds in the quality factor, which is Q, and that tells us how sharp or how pure the resonance is. And here's the reassuring bit. If Q is greater than, let's say, 10, uh, this correction is very, very tiny. we're talking about less than 1% off. So most of the time, you're safe to stick around with the ideal calculation. So you're going to be pretty close with the ideal formula. But when you're building high precision filters, communication equipment, or you're working near resonance sensitive systems, that 1% might just matter. So that 1% might be a big deal in that little world. So just take that into consideration for the real world. Coming up next, we're going to wrap this set with a final look at how real world parallel resonance behaves. I think I'm getting better at saying real world. And we're also going to talk about when it's time to worry about that current that shouldn't be there. So keep your multimeters close. We're not done yet. Wrapping up parallel resistance, slide 4 of 4. And here we are, wrapping up our exploration of parallel resonance with a tidy checklist of takeaways. And let's go ahead and keep this simple. Capacitive and inductive susceptance are equal at resonance. That's the condition that sets everything in balance. The total impedance peaks, and I mean ideally, it goes to infinity. In real life, not quite, but it's definitely the highest point on the impedance curve. So with that peak impedance, we get a minimum current. Power sources love that. So low current, less strain. The phase angle between your source voltage, which is denoted by V sub S, and the source current, which is denoted by I sub S, that hits zero. You have perfect alignment, no lag, no lead, just unity. And the formula to find a sweet spot, well, you know it by now, you know it by heart, is resonant frequency is 1 divided by 2 times pi times the square root of LC. And this is what makes parallel RLC circuits a cornerstone of filter design or for radio tuning, and my favorite, which is medical electronics. So wherever sharp selectivity and control over frequency response is needed, resonance is a big part of that. It's there. And that's it for this part. If you're like me, you're already imagining the real world circuits that this theory is useful for. Again, mine are mostly focused on natural phenomenon like medical engineering or maybe even in agriculture. That's just my area. But go ahead and stay curious, go ahead and stay charged, and I'll catch you on the next session. Let's continue with exploring series parallel RLC circuits. This is slide 1 of 2. Welcome back, explorers of electricity. Today we're diving into one of the most flexible and widely used configurations in all of AC circuit analysis. That's the series parallel RLC circuit. And we're going to set this up for you. So you've got an inductor and a resistor hanging out together in parallel, and they're teamed up in series with a capacitor. It's like the classic detective duo who split up to cover more ground. Only this time the mystery is impedance, right? Here's the trick. Even though this looks a bit more complex, the process is just an extension of what we already learned. Nothing here is new. It's just putting all the steps together. So let's go ahead and start with the parallel section that you see there in that yellow box. So calculate the combined impedance of the resistor and inductor. Then you can add the result to the capacitor's reactance since it's in series, and keep your complex number toolbox ready because you're going to need both real and imaginary parts to solve this. We're dealing with magnitude and phase, so this is where the math gets rich and the insights get even deeper. So if you're ready to calculate the total impedance, the numbers await us on the next slide. Let's go ahead and go. Solving a series parallel RLC circuit, slide 2 of 2. All right, class, pencils ready, calculators primed. Does anybody need to sharpen their pencil? Okay, because let's go. It's time to crack the numbers behind this series parallel RLC circuit, and we're going to break it down for you. We've got an inductor, L being 700 microhenries. This gives us a reactance, X of L, of J 0.880 kiloohms. We have a capacitor, C at 2700 picofarads, and this gives us a reactance, X of C, equal to negative J 0.295 kiloohms. And in the yellow box, that's our parallel team, a resistor with R equal to 1 kiloohm, and that same inductor. So let's go ahead and plug and chug, right? So plug this into the formula for impedance of the parallel elements, where you have the impedance of the box, right? So Z box is equal to R times X of L divided by R plus J X of L. And that gives us, if we plug in the numbers for the box, 0.436 plus J 0.496 kilo ohms. Boom, right? Now we add this in series with the capacitor's impedance. So the total impedance is going to be X sub C plus whatever Z of the box is, and that gives us negative J 0.295 plus, again, 0.436 plus J 0.496. And again, all we got to do now is just combine the like terms. So combine J's together and combine reals together, combine imaginaries together and combine the real numbers together. And with that, you're going to get, in polar form, Z total being equal to 0.480 at an angle of 24.8 kilo ohms. Now notice that I didn't break down all the individual steps that you see up there. I went ahead and skipped some steps. If you need to know how to go from rectangular to polar, go back to the previous episodes where it does show you how to do that. I'm going to be skipping that for the sake of time, so I don't have another 2-hour podcast. That's really long. All right, so that's our final impedance, the magnitude and the phase. Notice how the capacitor's negative imaginary reactance pulls the phase down, but the parallel inductor resistor pair lifts it back. So the result is this modest positive phase angle, just shy of about 25 degrees. And there's a real world insight. Real world insight. This kind of analysis is what lets you design filters, again, lets you design tuning circuits, and a whole much more. And it all comes from combining the fundamentals. So next up, we're going to explore what this means for voltage and current across each component. But for now, just take a breath, because I'm talking very, very fast, and it probably makes you anxious. So take a breath, review phasors, go back to reviewing phasor addition if you need, and keep those complex numbers close. You're building serious circuit intuition by following along. Bandwidth in resonant circuits, slide 1 of 2. All right, let's bring the spotlight to a term that pops up all the time in electronics, and that term is bandwidth and how it behaves in resonant circuits. So imagine, if you will, imagine, hurry up. Okay, good. So you're tuning into your favorite radio station, smooth jazz, classic rock, paranormal, ghost hunters, all the things I like, right? So if you're in class, it's most likely what you're going to be hearing. It doesn't really matter. The radio's tuned into a specific frequency, but you're going to notice something. If you drift too far away from that sweet spot, the signal starts fading. That sweet spot in a series resonant circuit, that's where the current peaks. That's where you get maximum resonance. It's that golden frequency, F sub R, where everything's aligned and the circuit impedance is at a minimum. But there's a kicker to this. The real magic happens in the zone around that peak, and that's what we call the bandwidth, or it's denoted by BW. BW. Yeah. And so this is the 70.7% figure, right? It isn't random. That number isn't random. It's tied to the point where power drops to half. We call it the half power point. Um, it's also called the half power frequencies. Right? So these are your f sub 1 and your f sub 2 on both sides of that graph there. So together they kind of bracket the usable frequency range for your resonant circuit. So not being at one specific frequency, but a frequency range where you get the, uh, not ideal, but the best before you drop to 50% of the power. So f sub r, don't forget that, that's right in the center. So the bandwidth being equal to f sub 2 minus f sub 1, that's just going to be the difference, the total length between those bandwidths, between those frequencies. Again, that's a spread where your signal is strong, clean, effective. And if you're thinking this sounds a lot like filters, well, yeah, you're right, it is. This principle ends up being the backbone of filters, the backbone of tuners, amplifiers, and a whole bunch more. And with that said, just stay tuned because next we're going to see how bandwidth is calculated using circuit values and how sharp or how wide that peak can get. And you're right in the signal path now, and the clarity is just getting started. Bandwidth in parallel resonance, slide 2 of 2. We're back and now we're flipping our perspective. Last time we talked about series resonance where current reaches its max. This time it's the parallel resonant circuit. And here's where things get interesting to electronic engineers at least. At parallel resonance, the circuit flips the script. So instead of current peaking, it drops to a minimum. Impedance, what about that? Well, it goes sky high. The circuit resists current flow at its resonant frequency, and it becomes what we call a tank circuit. And not because it's sluggish. Think energy storage. A tank circuit stores and transfers energy between the inductor and the capacitor, kind of like a slingshot being pulled back and forth. Right? Energy sloshes between the magnetic field of the inductor and the electric field of the capacitor. And again, just like before, we still care about the bandwidth, but now it's defined in terms of impedance and not current. We're looking for the frequency range where the impedance stays above that 70.7% of the max value. So again, same thresholds, different variable. So again, imagine this, and I know you're imagining now because I've stressed it enough. At resonance, the current takes a dip, but the circuit is fully charged. It's literally charged. It's holding energy. It's not dissipating it, and that's what makes it such a vital building block in radio receivers, oscillators, and again signal filtering. And here's another analogy, right? So for parallel resonant circuits, they're the quiet spots in a noisy band. A band, I don't mean like a band that's playing, I mean the bandwidth. Right? So when everyone else is shouting low impedance, high current, this one stays calm. It listens, it stores, and it resonates quietly. So again, let's keep exploring how this principle plays out across filters, quality factors, and practical circuit design. Trust me, we're not done yet with resonance. Selectivity in resonant circuits. All right, class. Here's where your resonant circuit earns its stripes. So it's called selectivity or selectivity. I keep saying selectivity. Imagine you're tuning an old school radio. If you don't know what one looks like, go ahead and Google that. And you want one station, not the static or the overlap between stations. And that's what selectivity gives us, the ability of a circuit to say, yes, I'll take this frequency and reject the rest. So again, it's in the name, selectivity. And the math here is simple, but it's very powerful. The bandwidth equals resonant frequency divided by Q. Uh, so you see there in the formula, BW is equal to FR divided by Q. And what does this mean? So if Q is high, the bandwidth is narrow, and the circuit gets pickier. If Q is low, um, bandwidth widens, and it's like a sloppy bouncer at a nightclub letting everybody in. So look at the graph on the slide here. The narrowest curve labeled greatest selectivity is your highest Q. The widest one, that's the circuit with the lowest Q, and it doesn't discriminate. And the takeaway here, what is it? Well, high Q circuits are the snipers of the electronics world. They focus on a single target, target, and low Q circuits, they're more like floodlights. They're bright but imprecise, and the thing is, this concept matters in everything from wireless communications to audio filtering, especially in medical diagnostics. If your MRI scanner or ultrasound circuit doesn't have good selectivity, it's picking up all the noise and missing the signal. So next time you hear the phrase tuned circuit, remember that it's not just about frequency, it's about being selective and sometimes about being picky. And that's kind of what you need in some cases. So let's go ahead and keep going. Okay, so we've reached the point of our podcast where I just kind of review some of the key terms that we've discussed. And the first one is series resonance, a condition in a series RLC circuit in which the reactances ideally cancel and the impedance is a minimum. The next term is resonant frequency, denoted by F sub R, the frequency at which resonance occurs, also known as the center frequency. Parallel resonance, a condition in a parallel RLC circuit in which the reactances ideally are equal and the impedance is a maximum. A tank circuit, a parallel resonant circuit. Key terms continued. The half power frequency, the frequency at which the output power of a resonant circuit is 50% of the maximum value. The output voltage is 70.7% of the maximum, another name for critical or cutoff frequency. And the next term, or the last term, is selectivity, a measure of how effectively a resonant circuit passes desired frequencies and rejects all others. Generally, the narrower the bandwidth, the greater the selectivity. Get to the point where we do a quick assessment, a review in quiz form. So let's go ahead and go over the questions. So this is quiz question number 1. In practical series and parallel resonant circuits, the total impedance of the circuit at resonance will be which of the following? A, capacitive, B, inductive, C, resistive, or D, none of the above. Go ahead and pause the video. And if you return from the video, the answer for this one is resistive. So that would be C. Question number 2. In a series resonant circuit, the current at the half power frequency is which of the following? A, maximum, B, minimum, C, 70.7% of the maximum value, or D, 70.7% of the minimum value. Go ahead and pause the video. All right, thank you for returning. And the correct answer here is C, 70.7% of the maximum value. Question number 3. The frequency represented by the red dashed line in the graph is which of the following? A, resonant frequency, B, half power frequency, C, critical frequency, or D, all of the above. Go ahead and pause the video. And if you're back, the correct answer is A, resonant frequency. Question number 4. In a series RLC circuit, if the frequency is below the resonant frequency, the circuit will appear to be which of the following? A, capacitive, B, inductive, C, resistive, or D, answer depends on the particular components. Go ahead and pause the video. And if you're back, the correct answer for this is A, capacitive. Quiz question number 5. In a series resonant circuit, the resonant frequency can be found from the equation. I'm not going to read all the equations. You can look at them. Is it A, B, C, or D? Go ahead and pause the video. And thank you for returning. And the correct answer is B, which was resonant frequency is equal to 1 divided by 2 times pi times the square root of LC. Question number 6. In an ideal parallel resonant circuit, the total impedance at resonance is which of the following? A, 0, B, equal to the resistance, C, equal to the reactance, or D, infinite. Go ahead and pause the video. Thank you for returning, and the correct answer is D, infinite. Quiz question number 7. In a parallel RLC circuit, the magnitude of the total current is always Z. Which of the following is correct? A, same as the current in the resistor. B, phasor sum of all of the branch currents. C, same as the source current. Or D, difference between resistive and reactive components. Go ahead and pause the video now. And you're back. The correct answer was B, phasor sum of all of the branch currents. Question number 8. If you increase the frequency in a parallel RLC circuit, the total current does what? A, will not change, B, will increase, C, will decrease, or D, can increase or decrease depending on if it's above or below resonance. Go ahead and pause the video now. Thank you for returning. And the correct answer was D. It can increase or decrease depending on if it is above or below resonance. Quiz question number 9. The phase angle between the source voltage and current in a parallel RLC circuit will be positive if which of the following is true? A, I sub L is larger than I sub C. B, I sub L is larger than I sub R. C, both A and B. Or D, none of the above. Go ahead and pause the video now. Thank you for returning, and the correct answer is D, none of the above. Quiz question number 10. A highly selective circuit will have a, which of the following is correct? A, a small bandwidth and high Q. B, large bandwidth and low Q. C, large bandwidth and high Q. Or D, None of the above. Go ahead and pause the video now, and you've returned, and the correct answer was A, small bandwidth and high Q. All right, thank you for doing that self-assessment. Go ahead and compare your answers here with the answers you've selected on the previous 10 questions. Also, don't forget, it's not just enough to know the right answer, but it's also important to know why the wrong answers are the wrong answers, as well as why the right answer is the right answer. Okay, thank you very much for your time, and I will see you on the next podcast.